Hey guys, welcome back. I found another cool problem from AMC 12B 2020, number 18. This one's kind of cool. It's a little geometry problem. Involves some similar triangles and knowing about 45, 45, 90 right triangles. So kind of a cool problem. In square ABCD, points E and H lie on AB and DA respectively, so that AE equals AH. Points F and G lie on BC and CD respectively, and points I and J lie on EH, so that FI is perpendicular to EH and GJ is perpendicular to EH. See the figure below. Triangle triangle AEH, quadrilateral BFIE, quadrilateral DHJG, and pentagon FCGJI each has area 1. What is FI squared? All right, so as you can see, I drew a little picture and tried to sort of annotate it as much as possible, label some sides. So let's just kind of see what we know. I want just to let you guys know, so by drawing this line here, I labeled this point here K, right, where this would be sort of a perpendicular line, right? And then what I also did was I also extended this line, this HJIE, I extended it out to here and then extended this line, CFB, to sort of create a little triangle down here, which you'll note also needs to be a 45, 45, 90. And the reason for that is because, well, the whole thing's a square. So when this is sort of cut to be 90 degrees, and we're told that AE equals AH, so then we know that this is a 45, 45, 90 right triangle HAE. So when we draw this triangle here, and we know like this angle here is 90 degrees. We also know like this angle is equal to this angle, and then this angle must be, because these two triangles must be similar. So then we know this is another 45, 45, 90, which I'll come back to that in a minute. But because we know that this triangle here is an area of 1, the only way that that's possible is if the two sides are both square root of 2. So AH has to be square root of 2, and AE also has to be square root of 2. And then because of that, now, because we know like each of these 4 parts has an area of 1, then that means that the area of the entire square has to be 4, which means the sides have to be 2. So AD has a length of 2, and AB also has a length of 2, which means like DH would have a length 2 minus root 2, and EB would also have a length 2 minus root 2. So now what you'll notice is I drew a triangle over here, a really very not the best looking triangle ever, but basically this triangle that I drew on the sort of right here is triangle C. So it's like CFBL. I call this point L right out here. So it's like CL and then KL being like this length here, and then CK. So basically it's like this triangle here. If you guys can kind of see what I'm talking about. So I sort of reproduced that triangle over here. Now, how did I know that the length of CK was 2 root 2 minus 1? Actually, the truth is it actually doesn't really matter what this length is, but the reason I know that is because, again, by looking at this triangle, knowing it has an area of 1, and I know that the hypotenuse HE would have to be root 2 times root 2 because it's a 45, 45, 90 triangle. So therefore, HE has a length of 2. So if I were to do half base times height using HE as the base, then the height AK would have to be 1. And because this is a 2 by 2 big right triangle over here, CAB, right, then that means this whole hypotenuse of the entire square is 2 root 2. So then the length CK has to be 2 root 2 minus 1. But I don't think that even matters to the problem at the end. Basically so really all I needed to draw was triangle FIL. I didn't even need to really draw the CK part, but I didn't know that until later. So I know that, well, what do I know? I know that the area of this, the area of this quadrilateral here is 1, right? I know that. Now, what else do I know? This little sort of right triangle that I added here in blue, well, I know that this length here is 2 minus root 2, right? Which I explained before why that's the case, right? And because I know this is a 45, 45, 90, even though it really doesn't look, I didn't draw it the best, then that means that like BL also has to have distance 2 minus root 2, right? Which again, based on the, again, it actually doesn't matter what the length of EL is. It's enough just to know that EB and BL are both 2 minus root 2. Because then what that can do is that can give us the area of this little blue triangle here, triangle BEL, right? If I do 1/2 times 2 minus root 2 squared, right? If I do 1/2 times 2 minus root 2 squared, which would give me the area of triangle BEL, that gives me 3 minus 2 root 2. So this triangle has area 3 minus 2 root 2, right? Which means that the area of triangle F, what is this? This is I, right? The area of triangle FIL in this case, right, would be 1 plus 3 minus 2 root 2, right? 1 plus 3 minus 2 root 2, or 4 minus 2 root 2. It would be the area of this triangle here, right? But if you think about it, this is also a 45, 45, 90, right? Because again, we know this angle is 45 from before. We know this is 90. We know this also has to then be 45 because we know this angle is 45 degrees. And this is a similar triangle. So it also has to be 45 degrees. So therefore, this would have to be equal to 1/2 times the height of the triangle squared, right? Because FI and IL are equal. So this could be equal to 1/2 FI squared. Remember, FI squared is what we want. So all we have to do is multiply both sides by 2, and we get FI squared equals 8 minus 4 root 2, and that's the answer, right? So I thought that maybe that might be one of the easiest ways to do the problem, but maybe you guys might find a way that's a little bit more creative, more interesting, easier, nicer. I'd be very interested to know if anyone finds a cooler solution to that. But I thought it was kind of an interesting problem, kind of cool, because you bring in sort of similar triangles and knowledge of sort of, isosceles right triangles. So pretty interesting problem. All right, so let me know what you think in the comments. See you next time.